My name is Christian Martin, and I'm here with Arista Networks. And I'm going to talk a bit about internet scale networking and the future implications for learning technologies and research networks. I'll be joined through the presentation with Warren Belkin, and he can introduce himself as we go through. Just a brief background, I have about 25 years experience in industry. Started my career at Lockheed Martin, and then spent about 8 years at Verizon building big networks around the country. I've done some consulting, and then have spent the past 10 or so years working in the supplier side, both at Cisco and Juniper before I joined Arista. So I have a lot of experience building large-scale networks and understanding the technology shifts that are underway as we start to move towards a more software-defined future network. So I'd like to talk about that, and I'd like to start with a bit of history here. One of the topics here will be software-defined networking, but I'd like to talk about how software-defined networking has really transitioned into what we like to call software-driven network automation, because that's really what's happening, and it's really being driven by the large-scale hyperscale cloud operators. So, SDN is about 10 years old. So when you look at SDN at 10, we think, what's happened in a decade? And a lot of what's happened really has been a transition to cloud networking. And when we talk about cloud networking, we're talking about, building big dynamic networks that scale globally, that meet a variety of new requirements technologically, and introduce a lot of new technology, and do so in a way that's highly automated. When we think about automation, we think about traditional networking, and then we look at cloud networking. The first thing we think about is just how we do network operations. In the traditional sense, manual box-by-box operation was the norm, and that had been the case probably throughout the growth of the internet, let's say. Some of the telephony networks, certainly the phone network, had a fair amount of process automation, but most of the work was still done quite manually, although there was a lot of support systems in place, a lot of technology to provide that support. As we moved into the internet, we did a lot of box-by-box and manual operation, but now, as these large-scale cloud network operators have built out their systems, built out their massive data centers that require a significant amount of connectivity, we're starting to see a network-wide automated operation where you have one or two maybe software engineers or DevOps engineers. Now they're called site reliability engineers, and they're using software tools to manage large-scale networks. In fact, you could argue today that, especially in the cloud, network engineering and network operations are really more about software engineering and software operations than they are about the traditional cabling and configuration management of network engineering that was done in the past. We've also moved from closed architectures towards more open and standards-based approaches. Now, that's not to say that there have been closed architectures, throughout the history of networking. Not, certainly far from it. Most networking technology is standards-based, but the means by which we do network operations has been closed, as anybody who's spent any time doing it would recognize. And that's largely because of the vertical integration from the system suppliers and the stacks that they provide, and then the network operational tools that are provided as the sort of counterpart to those technologies. And that still is the case today in the telephony environment, even though the telephony tool chains are, and the telco tool chains, I should say, are standards-based. So what we're moving more towards is an open standards-based approach, that the key aspect here being open versus closed, where the technology tools and the techniques are broadly available and well understood as a result of the massive amount of investment by these large cloud operators. And what I mean by the investment, I'm talking about the investments, for example, that Google has made and made available to the world through open sourcing, things like Bigtable or MapReduce and Hadoop, onto how some of the next generation telemetry technologies are done, and even how next generation automation is being done. So we'll talk about those technologies. Traditionally there was limited integration and control of the systems, right? You could control them only within the way they were parameterized for control. So there was basic configuration, and whatever was available in the software and whatever was configurable, and that as determined by the supplier of that technology, was really the bounds and the sort of sandbox that you could work within. But now, because you have programmability and you have API access, let's say, into the fundamental internals of the system, now you have a lot more capability, a lot deeper control, and a lot deeper programmability at all layers of the stack. So it could be at the application layer, could be at the protocol layer, for example, or it could be down at the hardware layer where you're actually programming some of the hardware in very specific ways. And then, of course, the skill sets have changed because traditionally, networking, although traditionally a computer scientific discipline, had as much electrical engineering and network science and operations research as part of the sort of the capability set that would be needed to be highly structured and skilled at network engineering, has now become more about software, virtualization, DevOps, being able to understand how to do continuous integration and continuous deployment. And it's really a software game at this point, even though fundamentally the network technology is still there. And part of the reason why this has been happening is because of the consolidation around a very select set of technologies that have emerged after 30 or 40 years as the winners. One of those would be, for example, Ethernet. Another example would be the internet protocol and IP in general. And then still another example would be some of the more specific technologies that are associated with building big networks, like the leaf spine architecture that is used inside of a data center, for example. So when we look at these technologies and then we think, well, okay, that's great. You know, we have these transitions from legacy networking to cloud networking. You know, what has that bequeathed to us? And really what's happening at the same time as these transitions are occurring from legacy networking to cloud networking is a re-architecting of the internet. And as everybody's probably well aware, most networking technology starts in the internet first. The most advanced and sophisticated technologies that are deployed in research environments, for example, or campus networks or large enterprises, are technologies that emerge from the internet, because the internet still is the big incubator. And that includes now, of course, the big cloud operators. You know, traditionally in the internet, we had, you know, the rise of the web, let's say. So that started, you know, as the transition away from bulletin boards and the early internet, the research internet of the 80s, and maybe even in some ways the 70s, but mostly the 80s and the early 90s, transitioned first into the sort of AOL CompuServe technologies that we saw in the mid 90s, towards the rise of the World Wide Web as we know it today in the late 90s and the early 2000s. And that's where e-commerce came online, where people were still using desktop computers. Laptops were largely not available at the time, and or they were, but they were generally not used the same way they are today, because of, you know, we didn't really have a mobile internet. And we had many-to-many connectivity at the time, but that many-to-many connectivity was really driven in a client-server way. So most consumers of the technology were going after content that was available on the web, and that the content was largely static. Now we live in a world where we have cloud-driven mobile internet, where everybody has a mobile device. The vast majority of technology is consumed in a mobile way. And the content is becoming ever richer. It's becoming sourced from everywhere, not just from, you know, centralized cloud servers, for example, but there's more content, for example, that comes from users than from traditional content houses. Services are all over the top, you know, so now people are, as everybody's aware, are able to access content in whichever way they want and purchase it. They can curate their content in their own ways. All the consumer technology is largely mobile, and there's just a massive amount of scale and a massive amount of bandwidth at play. And when we say scale, we're talking about things like device scale with Internet of Things, and we're talking about, you know, performance at mega scale as well. So some of the largest cloud networks have millions of servers in them, and, you know, the networks span the globe and have extremely high capacities. And this is something that will continue to evolve over time. And when you think about it, you know, the network technology that of the past was built for the traditional internet, and that technology still exists today. And we're transitioning away from it or into a newer paradigm of technology, such that if you really think about it, and if you think about what would, you know, if the internet were to be built today, not 30 or 40 years ago, but if we were built to be built today, it would be built differently. You know, in the past, there was just a different expectation and a different set of use cases, and they have changed. So what has to happen is we have to sort of transition away from that traditional thinking in order to be able to get these research environments, research networks, and learning environments into this sort of cloud age that we're moving into today. Now, there are new routing architectures and new network architectures driven by this move towards cloud, and this not just a move towards getting content and getting capabilities in the cloud, but from the cloud has such such an influence over our industry, because they drive such economies of scale. When I say they, I mean the cloud operators and the cloud technology, that the connectivity required is shifting. You know, we talk a lot about WAN networks, for example. And of course, in an environment like ASU or just general in the research and university environments, you still have campus networks and you still have wide area networks. And there's still a requirement for connectivity between campuses, for example. But more and more, a lot of the content is moving more and more towards the cloud. So now there's a change in the overall technology and the overall architecture, and that has an impact on these hotspots. And these hotspots tend to be where a lot of the attention is focused. So things like providing dynamic bandwidth and dynamic connectivity, to be able to provide differentiated services and differentiated connectivity, to be able to provide federated control between disparate organizations that don't have the same security posture or the same common identity management capability. All of these functions are being driven by this new cloud approach, and this will bleed over into the research and education environments. There are also market drivers which accelerate the transition from legacy networking to cloud networking. I'll touch on some of them. They don't necessarily all have direct access or impact rather on research networks or on learning environments, but they do have indirect impacts, and they will have an impact on the decisions that networking professionals in these environments have to make. One of them, of course, is the 5G technology revolution that we're going to see really start to take off over the next 3 to 5 years. So much more bandwidth, high scale IoT. So this is already happening, but it'll happen at a much higher pace where you'll have 5G based IoT, not just Wi-Fi based IoT. And then higher bandwidth and lower latency is going to be key. So with the ability to now have wireless connectivity almost anywhere on the planet at high bandwidth with low latency, and that'll happen over time, a whole new set of applications come online, and a whole new set of challenges and capabilities will have to be put in place to meet these new technology requirements for these new applications. Content providers are becoming, as I mentioned, more and more differentiated. They're becoming much more structured towards providing better services and differentiated services, and that is driving a lot of bandwidth and a lot of technology change to ensure, for example, high quality and to make things like digital advertising and targeted advertising more effective. So that becomes part of the technology landscape. Broadcast and production, in order to create, we're already seeing this now. I'm old enough to remember when, there were like 3 or 4 channels on the TV, and then you had cable TV that added maybe 20 more channels. Now we have countless numbers of channels, and it's not just channels. We talk about channels because that's the original broadcast mechanism where we channelize the broadcast medium and the overall bandwidth. Now we have content coming from everywhere. And that means we have more broadcast and production requirements, and that has a new technological impact on how networks are built as well, because there are different ways of providing this content, and there are different capabilities needed to deliver the content at scale with the quality expectations that people have. Research and high tech is another area, particularly around machine learning and artificial intelligence, and then on high performance computing side with cluster computing. These are 2 areas where you'll see a greater push towards more exotic technology, and certainly a much more intensified look at how data is moved around. And that has a huge impact on the network. One of the things that you see a lot of discussion around is just the cloud scale of the big cloud operators. And if you take an operator like Google and think about what their sort of production, internet-facing bandwidth requirements are, those bandwidth requirements are fundamentally bounded by the total bandwidth consumption available in the internet. So like if you think about YouTube, for example, the amount of bandwidth that Google serves is the amount of bandwidth consumable by all the users in the network. But that total bandwidth, which is, let's say, some subset or portion or percentage of the total internet bandwidth that's used or consumed, is a fraction of the amount of machine-to-machine traffic and the machine-to-machine bandwidth between servers in these large environments. And that's largely because of machine learning-driven data sets. So all the things that we now take for granted and almost don't even notice requires a massive amount of data. And obviously people in the research and education community know this, especially if you're doing research around artificial intelligence. But this is a massive driver because this is really what's driving our accelerated push towards higher and higher speeds at a pace that has been unmatched before in the industry. I remember when the first 10 gig interfaces came online, and that was in the beginning of the 2000s, right? This was in the Sonnet world, this is OC192, is a 10 gigabit per second interface. And that interface and that line card, for example, that would plug into a router costs almost $1 million, and that's for a 10 gigabit per second interface. Today, you can buy a 10 gigabit Ethernet switch to put in your house for $100. And so there's just dramatic reduction. And part of the reason for that is there's so much bandwidth requirements in the cloud. Likewise, on the enterprise and financial services side, there's a lot of advanced technology that goes into enterprise and FSI specifically. Some of it is sort of virtualization technology. Some of it is hardware-based with field programmable gate arrays that gives you a whole bunch of new capabilities. And then, of course, the storage requirements for enterprises continue to increase apace, such that now one of the cloud operators, in this case, Amazon's most popular services, is something called Snowmobile, which is literally a truck full of hard drives that backs up into your data center or to your corporate headquarters. You plug it in and it sucks all the data out of your network or your data center so you can migrate them to the cloud. So, storage is a big part of this. And of course, network-based storage has impacts on network designs as well. And then managed hosting. This is something that's not just hosting, but we think about this more as just platform or infrastructure as a service, which is really what drives a lot of the cloud technology. And you need some security around this. You need analytics. You need to be able to support next generation technologies like gaming, which not only have storage and processing requirements, but also have proximity requirements to reduce latency. So this gets into things like you may have heard of like edge compute or MEC, which is the mobile version, mobile edge compute, which is part of the next generation architecture. So all of these aspects of the market driving the industry forward will have impacts on the technologies available to research networks and to learning environments and learning networks or institutions of learning who are trying to build technologies and build capabilities into their environments to enable and accelerate the betterment of these environments to achieve objectives for the university or for the learning environments and institutions themselves. So Warren, why don't you jump in here and talk a bit about what's happening on your side and what you're seeing with ASU and some of the other folks that you're talking to.
Great, thanks, Christian. My name is Warren Belkin. I'm a regional director in the Southwest here for Arista, and I work with ASU on a number of these types of technologies. Christian's given a very interesting backdrop to sort of internet and hyperscale networking and cloud, and where does this tie into the educational environment? Clearly, future learning modalities are moving to very immersive experiences, whether we talk augmented reality or virtual reality. There's a lot of much more immersive experiences, and all of these things have very heavy demands on the network. Most of them today would not operate correctly in existing campus networks that were built 10, 20 years ago. And so there's a lot of thinking that has to happen on the infrastructure side of what would you need to do to support these types of applications that are coming in the future? And how do you share expensive assets that a university might have? Go ahead, Christian, could you switch to the next slide? And really the real question here is how do you do that across on demand? So you may have needs to do this, but the network's not going to support all of the services required on a full-time basis. So there has to be some dynamic capability to provision services across the network. What does that mean? It may be bandwidth that's required for an AR session. It may be latency requirements. It may be virtualized networking. Do you need a layer 2 adjacency? There may be security concerns. There are all sorts of network services that have to be provisioned to support a given educational application. And the question is, how do you do this? When you have these things being used in a large-scale learning institution, you can't rely on a help desk to go provision this. And that may be what happened historically. So let's take research as another example. In research computing, there's a desire to share high-performance computing clusters or share data sets that may have come across from an HPC project. And today, that's pretty much a manual process. Someone's going to have to request and have approved for access by someone else, and you're going to have a hole in a firewall set up somewhere to allow this to occur, and the right assets put in the right modes and shared. Well, all of that just doesn't scale when you're relying on a human help desk to do this. And so the implication of all of this is you really need to automate to make this happen much more in a cloud-like world. So I think the real lesson here is the demands on higher education and education in general, IT is going to start looking like the public cloud. Go ahead, Christian, to the next one. Sorry, go ahead, one more. Thank you. So when we look at a typical higher ed institution, there's going to be a desire, and this is something ASU has talked about, a very aspirational vision around this. And it will take some time to make this sort of fully realized. But think about what an educational institution has that they might share. There's very expensive equipment. You might have a scanning electron microscope that costs $1 million. How do you share that amongst other campuses within your own institution? And how do you share that across partners that might be in a regional education network? You might have, as I said, HPC clusters, compute clusters that you want to share. There may be data sets of things you've created. There's a whole bunch of reasons why you want to share this either within a single campus, across multiple campuses in a single institution, or multi-domain across different partners. And when you think about that problem, it starts to look a lot like a cloud. So first you have to define what these things are that you might want to share or give access to. So you need some kind of resource catalog. And part of that resource catalog is tracking what does that particular asset or application or device need from infrastructure to be able to work properly? What kind of latency and bandwidth and security? And there's an aspect of identity. Who's trying to share this thing? And then there's the whole governance piece. Who's allowed to share this? What are the times of day? What kind of security is required? How do we log and audit what's actually taken place? And then some kind of self-provisioning portal to gain access to these assets at a scheduled time. And all the workflow management that might be required for any approvals on that and monetization. But at the end of the day, when that's all done, this thing has to automatically provision the infrastructure to deliver the requested services. So this is really around, very similar to a cloud, automatic provisioning and automation of infrastructure without human intervention, so that you can scale this and make it very seamless and deliver it very quickly. Go ahead, Christian.
Thanks, Warren. So a couple of things I'd like to draw from the world of SDN as it was originally envisioned and what's happened in software-driven networking over time. And as I mentioned, it's really transitioning towards software-driven network automation. So it's really SDNA, but let's talk about SDN to date. First of all, there's a lot of new faces. And SDN, excuse me, has morphed a bit because originally it was about research networks, particularly about computer scientists and people who are in networking research being able to use existing network infrastructure on the campus to be able to, experiment with new, networking technologies. And then it transitioned from that into like a way to commoditize and disaggregate the hardware and software from each other, the traditional solutions that were being provided by the large system vendors like Arista or Cisco or others. And then it sort of become ways for us to build data centers and overlay and underlay networks between different parts of the world or different parts of a data center and then extending it. And now, so we have something like a software-defined WAN, which is its own sort of industry at this point. The software-defined data center. This is something that is deployed almost everywhere. Software-defined evolved packet core environment. These are used in the 5G and 4G environments, and so on. The key word here is software. And it's funny because we talk about SDN as a new concept, but software has always driven networking, right? The hard part of networking is not necessarily the hardware. I mean, the hardware, that's a challenge, of course, but the true hard part to be, and this is coming from somebody who spent 10 years, on the vendor side, helping to build software and solutions for new technologies, for networking technologies, et cetera. It's hard to get the software right. The software is very complex. And so one of the challenges and one of the things that we have to keep in mind is that software is the key word here. And how you use that software, how you use the programmable interfaces that you have will really drive your technology adoption strategy. And will also, I think, have a lot of impact on the success you have. SDN is not really about cost reduction. This is something that was really the way a lot of telecommunications operators and maybe network operators in general started to think about the technology, because they saw a way for open source software to converge with commodity hardware and reduce the overall cost. But really what it's about is service market and value expansion, and particularly the value expansion piece, because, value expansion does not just mean, being able to improve the bottom line. It means, can you gather and gain more value from the infrastructure you have, whether that's better learning opportunities, more sophisticated learning opportunities, better research networking, research opportunities in both networking and in general. Warren's example with being able to leverage or access, an expensive and highly, rare piece of equipment is something that's a good example, I think. And the value of of learning environments, I think has become very, very acute for almost every parent that's on the phone right now. If there are any parents, I don't know if it's mostly students or if they're researchers as well, that's on the conference. But for me as a father, I've watched my son and his classmates spend the past 3 months during COVID, being able to learn remotely. And he's on a Zoom call every day, just like this, but he's with his teachers and he's learning the things that he learned. So it's interesting to see that. And it's a simple example, but without the cloud, this would not be possible. So all of the things that we've just talked about, have enabled this new capability. As I mentioned, much of the SDN value today is around automation and service creation. So, you can launch services fast or launch capabilities fast, make them easy to operate and capture new opportunities. And the most critical thing, and I'll touch on this towards the end, is to gain experience early. Far too many organizations are sort of mired in this indecision or this sort of waiting game to wait for the technology to mature enough where it can be applied in a very significant way. But there's so much value in incremental experience, because what really has to happen in order to build a software-driven automation environment or software-driven network environment is to build a culture of software excellence. And that cultural endeavor, embarking on that process, is not just something you can do easily, right? It requires a lot of thought and a lot of practice, and then some failure, and then some adjustment, and then some more practice and some more failure until you get it right. And if you can create a culture of software excellence with a value creation mindset, not just with a cost-cutting mindset or with a sort of protectionist mindset where we don't want to risk any outages, or we want to make sure that the network is stable, for example. Those things are all important, but you don't get much value out of software-driven network automation if you're not willing to let the software drive the network. And in my experience, especially working with telecommunications providers, that's one of the largest hurdles. It's a cultural change that has to happen. So let's talk a bit about this and what we've seen, at Arista, and in, my experience generally, in my role, I have a global responsibility for what we do with service provider customers. And our service provider customers span the largest telcos around the world. And all of them are in various stages of their journey on this path towards a more automated environment. And there's a life cycle. There's an interdependent life cycle, as always is the case, where you have time and business priorities or technology priorities or organizational priorities, the available expertise and the amount of money available, kind of working in concert, and sort of cyclically going through these sort of iterations through technology and process and expertise. And do you have the right people? Is there a budget? All these are parts of it. And there are some considerations that any organization who's looking at becoming able to automate their environments and get that scalability, that rapid deployment, that functional capability you have to consider. So what is desirable? What's the cool stuff? What do people think that we need right now? And that is really a fully orchestrated end-to-end automation of all services. Now that sounds like a very big and lofty goal, but this is how the largest cloud operated networks are run, right? So when you hear about a data center with 10,000 devices managed by one engineer at Facebook, that's not an urban legend. That's actually true. Now they have a lot of symmetry and a lot of sort of cloned technology, a lot of sort of geometric symmetry, and a lot of repetition and replication of the same functions. But they still have the willingness to allow software control over their entire infrastructure, and that's a big part of it. What's practical? Short staff deployments in need of some quick and dirty scripting to get you through to the next deployment. Well, what does that mean? A lot of times, what we're trying to do is just get things out the door, and there's a lot of pressing concerns. So you have to be able to carve away time to do the automation bits right, and then make them more and more part of your culture. And so that's why you aim somewhere in between. You, of course, aren't going to get to the panacea in the first day. And you can't just say, oh, I just need to hack something together to make it work. I want something in the middle. And you have to start with the data. And I'll talk about this in more detail later. But the first and most important thing that you need in order to automate anything in any environment is whatever parameterization you have around whatever parameters are involved in what you're doing, whether it's the network, where the locations are, the ports that are connected, the services that are running, the addresses that are used. All that data has to be meticulously cleaned. And that is a long and lengthy and sometimes painful process, because most network environments that I've been involved in have a lot of legacy, and they have there's a lot of skeletons and graveyards and tombstones and zombies. There's stuff that's laying around that has been there and nobody wants to take it away because they don't know what it's doing. And so that's something that everybody has to come up with and be able to reckon with, because you can't really get much further without that. When you look at the lifecycle, there's really 4 aspects to the automation lifecycle. You have deployment, where you're racking and stacking and cabling. Then you have provisioning, where you're sort of activating or you're bringing the technology up. Then you have activation, which is where you start to cut in the capability into the network. And then you have the day 2 and ongoing management, which is really where you evolve the configurations and evolve the services. And then throughout this whole process, you have testing. And in order to make the testing scale and make it work viably with this new automated environment, you have to automate the testing. It's one of the most important aspects of software engineering. It's something that we use at Arista to ensure that our software is of high quality and regression free, for example. But it's more and more critical for automated networks, because you have to not only automate the environment, but you're going to automate the testing as well. Now, there's a lot of tools available for us to do this kind of automation. On the deployment side, there's inventory management tools. We have something called Cloud Vision. There's lots of open source tools. There's commercial tools. On the provisioning side, ZTP is a technology that is now standardized, and there's a lot of console integration technologies, for example, so that you can plug in and touch every piece of the of equipment in a sort of out-of-band kind of way. On the activation side, there's a couple of protocols here and technologies I've highlighted. You probably see Ansible and Kubernetes here, and APIs and Linux. Those are all critical, of course, fundamentally. Netconf-Yang and OpenConfig are networking specific technologies. These are standards-based modeling and control languages. GNMI and gRuby, these are protocols that have been developed by Google. The network management interface and the routing information base interface, these allow us to control routing directly without having to communicate through protocols or even through a programming interface necessarily. And the network management interface gives us the ability to manage the network, change its configuration using OpenConfig models, for example. On the right over here, day 2 management, we have things like data analysis and buffer and queuing analysis. Notice that we have telemetry and analytics, also critical to this whole thing. Service assurance is part of it. And then I have another highlighted protocol here, GNOI, which is a network operations interface. So this is another Google interface, all based on Google RPC or protobuf, a technology that Google has made available to the industry that gives very rapid and very rich access controls over a total system management. And so this is something that is really where a lot of the benefit comes, because you have a ton of public experience that is, sort of shared in the open source community. So, models, for example, for configuring systems, for building large scale data centers, for doing quality of service and improving quality of experience. All of this stuff is available publicly, published by engineers at Google and Microsoft and AT&T, this gives you access to technology that's deployed in the largest and most mission critical networks in the world that doesn't necessarily touch on the original idea of SDN, which was, let's find a way to separate the routing protocols from the hardware. It's more about, let's connect the network together. We'll put some agents on these devices, and these agents will be able to leverage existing technology that's well-baked, and then merge it with new technology as it develops and as it evolves, so you have perfect backward compatibility. And it's an incremental approach that gives you all the access to all the cool stuff that the most sophisticated network environments in the world are using. So this is what we recommend. And of course, testing should be driven through some kind of automated framework. And there's one that we use that the industry has developed and sort of rallied around, called the robot framework, that's based on Python, which is the most practical and right now most popular programming language in the industry. It's something that's easy to learn for almost everybody. One of the things that comes up a lot is expertise. Because, as I mentioned earlier, you have traditional network engineering expertise based on data science and network science, operations research, and electrical engineering. with bits and pieces of computer science tied into a software environment that's much more computer scientific based, much more software engineering based. So how do we get people to transition there, especially senior people who've been in the industry for a long time and don't have those skills? And the best thing to do is actually to train some engineers who have the aptitude or the interest to become more software driven. And then as you start to, sort of cycle people through the organization, as people start to retire, you start to onboard new talent and younger people, then those people come in with a lot of software skills. And so you have a, sort of a continuum, if you will, of people with different skills, but you have to have both. And you have to have those. It's going to be hard to turn a bunch of network engineers directly into software engineers, but you can get them closer by learning some basics and then bring in other people who have the software skills. And then the networking people could teach them software, and the software people could teach the networking people about how to do automation. So I think that's the kind of symbiosis that you want to have. And the deployment pipeline is really important. So communication and version control and peer review, this is all cultural. This is something that you have to institutionalize in the environment to make the team work in a certain way. And there's a difference between the way traditional network engineers operate and software engineers, because software engineers have a whole different engineering paradigm than maybe network engineers would have. So it's something that has to be considered as well. I think development experience should be part of every team, so that you have a developer or a set of developers who are really good at it, professional developers, who can help the people who are onboarding and the people who are sort of becoming more experienced, understand the computer scientific aspects. And what I mean by that is, you can learn how to do scripting and you can learn how to do basic automation, but the real art and the real computer scientific art is the refinement, is the performance. Can you do it at the fastest, most efficient possible way? And this is the key aspect that you'll need in order to make things scale. On the process side, change management processes need to be secured. They need to also be ratified and ramified, if you will, by the organization. As you start to turn more and more control over of the network to the automation systems, the computers, you'll need ways to be able to break glass in case of an emergency and override the system. But you also need post-mortem capabilities, though of course they should be blameless. Otherwise you have a culture of blame, which will restrict your ability to take risks needed to make this transition. You need to have executive level buy-in, or the culture of, and a culture of accountability for all those people that touch the network. It has to be blameless, but there has to be accountability in that everybody who takes the network operations responsibility seriously understands the impacts that they can have, so that if mistakes are made, you can learn from them, and then those learnings can be reapplied to the next steps that you do, so that those mistakes don't occur again. If you don't have all this buy-in, if you don't have all these pieces in place, then automation will fail and the journey will stop before it even really started. In other operators, just the basic change management process with executive buy-in, a blameless postmortem culture with accountability across all changes. And that means that if, hey, look, again, it sounds sort of contradictory, like, hey, how could it be blameless with accountability? Everybody has to be accountable, right, for mistakes, but you can make a mistake and then not be blamed for that mistake. More specifically, not punished, embarrassed, or in other ways ostracized, or whatever it may be, because then people won't take the risks. You have to be able to make mistakes, but learn from them. And in the environments where we've seen these cultures put in place, we see greater than 30% improvement in operational efficiency and human error reduction. The last point I mentioned earlier is data hygiene. Data hygiene is critical. The biggest impediment to automation is a lack of reliable data sources. The sources for truth in the infrastructure are key, and there should be only one. There can be redundant sources, but there can't be multiple sources, because it's really hard then to federate those sources or to determine which ones are most accurate, which ones are most trusted. The gaps in data hygiene, or if there are problems, you get delayed processes. So if you haven't organized your data and put it in a way that's clean of any artifacts or any zombies or any sort of inconsistencies, then you get deployment of hardware delays, you have problems with infrastructure management, it's difficult to integrate into existing tools, you get issues with deployment planning and policy management. So it's really critical, and I've said this a lot to a lot of folks, as they start to go on to this process, one of the things you could start right away is just cleaning up your data, because that is a sort of a thing that you have to do anyway. And if you have any hope of doing any kind of really sophisticated automation that gives you that vision that Warren laid out before, of being able to create dynamic access to sophisticated tools on demand, for example, you're not going to be able to do it without clean data, regardless of what other tools you have. Now, we have a few minutes left. I just wanted to touch on some economic considerations. When you think about the value of automation versus the cost, you have value in that reduction of truck rolls and better mean time to repair, the elimination of methods of procedure documents and reduction of SLA violations. But then you have to onboard a DevOps team, and you have maybe some new integration and a lot of software engineering requirements that come into play. So when you think about it, is the value greater than the cost? And what we've learned is that it is, and it's actually significantly greater, but you have to be willing to make the upfront investment. One of the things that often is part of this discussion is, do we build or do we buy? Do we sort of build the capability in-house, or do we just kind of onboard it on the outside? I think it's all a factor of time and expertise. If you have the time and you're willing to develop the expertise for the long run, then building is better, right? Because not only do you build and onboard new capabilities, but then you create a new culture, and that something that you could perpetuate not only within ASU, but in the larger learning organizations that ASU is affiliated with. And that allows an organization like ASU to take leadership role in the larger learning community and help drive new technologies, which is very important, especially for I would imagine for recruiting, for getting the best students and the best minds. This of course helps, the sort of whole larger academic ecosystem around, being able to secure grants and funding and good projects, and to be able to get good visiting professors and all the other things that are associated with this. If you don't have time, or if there's a specific endeavor that you're trying to go after, it may not hurt to buy it and maybe do a build, operate, transfer, or buy it with a sort of an option to then build beyond that. So you kind of learn what you can get, and then you get a sense of what's possible in a supported environment that's commercial, and then you can move towards sort of a built-in in-house approach. And then, of course, one of the big considerations is, do you have the time and staff to upskill your organization? From a return on investment perspective, the areas of impact are clear. Sometimes they're not necessarily monetary, because we're really trying to make an investment in a not obviously tangible capability, right? So, for example, being able to enable more efficient or more spectacular research, really, to be able to do more spectacular things, to be able to do more sophisticated things, may not pay out in the short term, but it depends on what your metrics are. In terms of the network itself, however, the areas of impact are quite clear from the data. The one thing is the reduction in maintenance windows. You can reduce the amount of time a maintenance window takes, but you can also do more, and you can do them in more sophisticated ways, especially if you follow the cloud architecture principles and build a scale-out architecture rather than scale-up. Because when you have vertical integration, you have systems effectively in series, and we understand those to be less reliable than systems in parallel, intuitively and scientifically. So if you can parallelize a lot of the network architecture, then you can then take pieces offline and still have the same availability, and that reduces the amount of risk and therefore allows you to do more. So if you want to be able to create more dynamic connectivity or richer performance capabilities for certain activities at certain times of day, for certain applications or mission critical requirements, you could do that, especially if you have lower risk. Reduction of truck rolls. So when you break things, do you have to send somebody to fix it, or can you fix it remotely? SLA violations. You will reduce a lot of the network impediments and impairments that come online and are onboarded by human error through automation. MOPS are sort of a more, I guess it depends on the environment, but a lot of environments have instituted these procedures. Reduction in changes and deletes and improvement of MTTR, all are part of the ROI calculus here. How long does it take? A lot of things have to be aligned. I won't go through all the details, but this is more than just a technological endeavor. We're talking about influence building and cleaning up the network and maybe checking on a new org structure and doing lots of process documentation. So whatever you do, all of these things need to be considered. And of course, before then, small incremental successes will have to pave the way for the eventual adoption across the org, but you'll have to consider these things on the larger scale. And then where to start? Really, we're thinking about the combination of big impact and low complexity. You want early wins. You want to be able to do it relatively easily so that you could prove in the technological advancements and the impact to the organization. So what's realistic? What is something that you could do in the shortest deadlines? Who are the people involved, and what is the data available? Is there a way to do this that has a big political advantage and business important that's not risky? Sometimes that's hard, but these are things that have to be considered. So the final thought I'd like to mention here again, and just to reiterate this point, is that experience matters. You can't wait for the perfect time when the technologies finally emerge and you get the right sort of alignment of the stars. You have to kind of take a chance and do things, as I mentioned previously, maybe big impact, low risk, where you can kind of prove it in. There's plenty of value to be added now. Software-defined DCs are widely deployed all over the world. This is something that's part of the data center architecture of the present. But software-defined WANs, that's another example. Segment routing is a new routing technology that allows us to build very sophisticated and very specialized or very specific networking capabilities for a lot of different use cases on a common network that we could have never done before. And it's highly programmable. It's a perfect example. And again, SDN is about value creation. It's not a self-actualization exercise. A lot of the original, hubbub around SDN was, we'll be able to onboard and take away all the challenge and all the technology from these network suppliers who, take too long, or, their quality is no good, as if this was some kind of, mission, vision quest for an organization. Take the technology where it's good. If a supplier provides a good piece of software, take advantage of it. If you can build something similar or better, then do it. But don't create a sort of religious, sort of dichotomy between the present and the future, or the past and the future, and make that the decision point. Leverage the best technology available in a package that's ready to deploy, and get the experience when you can. So we think of SDN as something we can do now. And so take advantage of it that way. And I think you'll be successful in being able to actualize the goals that you have for the organization. With that, I'm finished. I think I'm a little over, but thank you very much for everybody's attention and listening. And if there are any questions, I didn't see any come through on the panel, but if there are, I'd be happy to answer them.
Yes, if anyone has questions, please type it into the chat window. We only have a couple of minutes until the end of the session, but we're happy to answer anything. I don't see anything coming in, but we want to thank everyone for attending, and hopefully there was some useful information on how this ties into higher ed and the goals for automation and kind of the next generation of learning applications and research collaboration. If there's anything we can do, please feel free to reach out. Our contact info, I'm sure, will be available through the Learning and organization. Appreciate everyone's time. Hope the rest of your day goes well in sessions, and hopefully get a break for some coffee. Thanks so much.
Thank you, everybody. Thanks, Warren. And thank you, Ashley, and the rest of the community. Good luck with everything.